Welcome to this video. We're going to solve number 14 from page 11 of your notes. So this is a problem on random and systematic error, and this is a little bit different from some of the other graphs you're going to see. How is this different? Well, the other graphs contain a dotted line showing you where the data should be. So it's easy to make a statement to draw a conclusion about random and systematic error. Doing that is easy when you have a dotted line showing the actual values, and then you can compare the actual values to the measurements. But what if you don't have a dotted line, as is the case here? Where is that dotted line? Well, you have to fill it in yourself. How do you fill it in? You look at the x and y axes, and you consider how the quantities are related. So the problem says a student conducts an experiment applying a net force to an object for a time t and measuring its final velocity. This problem should also state the object is initially at rest. So we need to add that in. That's something that was intended to be listed, initially at rest. And you can't really solve this problem without it. Now this is a hard problem, and I'm going to show you how to figure out what the graph should look like using this pretty difficult example. Part A. Write down the relationship between final velocity and net force. Hey, final velocity and net force, those are my axes. So they're prompting us right here to do exactly what they're prompting us to think about where the line should be. Okay, so what's the relationship between velocity, net force, final velocity? And it says think about impulse. What do I know about impulse? Well, I know impulse is equal to the change in momentum. P is what we use for momentum, and it's really the net impulse is equal to the change in momentum. And what's net impulse? Well, that's force times time, but net force because it's net impulse. And what's change in momentum? Well, momentum is mass times velocity, so change in momentum would be mass times final velocity minus mass times initial velocity. And something we're going to see a lot of, IB, for final velocity they use V, and for initial velocity they just use U for initial. Okay. Now, there's the equation. How did I get this, final minus initial? Well, every change, every delta, is final, P final, minus P initial. Every delta change in is final minus initial, and so I just did the final MV minus the initial MV. So that's how I got there. Now they say the initial velocity, U, is 0. Initially at rest means U, the initial velocity, is 0. So this whole thing is 0, and now we have F net times T equals MV. So let me, down here below, write this out. F net, I'm going to divide both sides by T and say F net is M over T times the final velocity V. Remember, final velocity is V, initial is U. So what's this say? Well, M is a constant, T is a constant, so net force is a constant times velocity, the final velocity, or in other words, net force is directly proportional to velocity. So the graph of net force and velocity, what was it? It's velocity on the y against net force. The graph should be, what's the graph of? Well, it should be the graph of a direct proportionality. Straight line through the origin. Okay, now that we know that, let's make a straight line through the origin. There it is. There's my straight line through the origin. Kind of straight. Alright, so now we can do our analysis. Is there a random error? Well, look at that fluctuation. I mean, this data is fluctuating around a line that looks something like this. So maybe that's the best fit line, and it's fluctuating. So yes, because the data And then you could say fluctuates above and below the best fit line or something along those lines. By the way, the green line is the best fit line here. The blue line would be the true values. In some of the problems you're going to see, you will be shown the blue line, and in some, you're not shown. You have to figure it out just like we did here. Is there systematic error in the data? And if so, estimate the size of the error. Well, is there systematic error? Look at this. Every single one of these data points has been, well, the green line, rather, has been shifted down from where it should be. So there's definitely some shifting. Every single data point has been impacted with some negative, we've subtracted off something from each data point, causing them to be lower. So yes, there is systematic, because every measurement of final velocity has been shifted down from where it should be. So what's the size of the error? Okay, what's that asking? It's asking how much has it been shifted down? What is that negative error? Well, it should be up here, and it's been shifted down, so it's a negative error, first of all. And then what's the amount? Well, let's try this. Right? From here to here, that's 1.5 tick marks, roughly. So we're going from there to there on the axis. That's 10 plus another half of 10, 15. So the error is somewhere around -15, and we've said that this is all of the error we'll look at in this handout will be vertical error. We're always shifting down or up. We're not going to be imagining a leftward. Do not imagine a leftward or rightward shift. Only imagine up and down shifts. So what's the unit for that upward or downward shift? Well, this downward shift in this case has units of meters per second, or meters second to the -1. There we are.